So the idea was to cover topologies and offloading. I'm gonna focus more on the topologies side. And then I think I have one slide on offloading just to give a tease, more or less. So topologies. I got it. So first, let's look on the networking perspective on the top 500 list. It's interesting, or it's makes sense to look on top 500 because it gives you the information about trends and what's happening throughout the history. So back to 2005, it works. 2005, it was, I think, 2 years after InfiniBand started, more or less. Was a much bigger take on proprietary interconnects, if you remember Quadrix or Miracom. And then Ethernet, which was gigi, maybe even less, was half of the list, more or less. And then throughout time, you saw that InfiniBand started to take over as being a standard solution. Let's make things more commodity, easier to access, multi-vendor. InfiniBand started to take over very nicely. First, it took over the proprietary solution that right now doesn't really exist much on the top 500 list. Cray kept the same take, more or less. But now InfiniBand and Ethernet kind of almost sharing half and half. So first, InfiniBand took over the proprietary. You see that one went down. And interestingly, it started to take over the Ethernet system, and it's going to be interesting what's going to be on the next list in June to see if InfiniBand will continue the momentum and take more, or they're going to stay or become equal. So that's kind of a trends. That was end. That was quick, yeah. Wrong button. Yeah, this one is a great question. By the way, you know that there are three kinds of questions, right? There is good, great, and interesting. The good question is something that I know the answer on. A great question is something that I know the answer on, and I have it on the next slide. And the interesting question is something that I want to know too. Right? So this one was a great question. So if I'm taking the systems and put them on the efficiency list, then you see here that I broke the gigi and the 10 gigi. Put them on efficiency list just to look on what kind of efficiencies different networking provide. Now this is the top 500 systems, right, ranked from 1 to 500. Maybe I should take the 0 out. And then basically we'll find same kind of CPUs, right, same kind of memory CPUs, more or less, in all of the systems. So it gives you a nice feeling on efficiencies. Now Limpac is not a great benchmark, or it's great. It's a good benchmark. It's not a great use from the application perspective, but still it gives some feeling on capabilities. So first here you see this is the gigi-based systems, which is more or less an average of like 50% efficiencies. Now there is many systems that kind of being broken into multiple pieces because Gigi doesn't really scale for Limpac when you go bigger systems. So some systems are basically the same system broken into multiple pieces. InfiniBand is here. I would say average probably 85%. The bunch here are the Cray systems. So you can definitely see that from efficiency perspective, InfiniBand and Cray, InfiniBand even can provide higher efficiency than Cray, but they're in the same range, more or less. The circles here, those are the 10 gigabit Ethernet systems. So they're increasing the efficiencies. I think there is one here somewhere on the lower part, but they, in average, they're increasing the efficiencies towards the 75% in average. There is a notion about IWARP, and is IWARP much better than TCP? From my experience, IWARP is a great option to try to bring, IWARP was a great idea to try to bring RDMA to Ethernet, but the big problem with IWARP is IWARP requires TCP. So if you require TCP, now you're back to all the overhead of TCP, so why do I need to run something on top of TCP when I can just run TCP? So this is exact examples. This is like a 10 gigabit Ethernet TCP systems, and this is an IWARP system. So IWARP doesn't really provide you any benefits in related to efficiencies. The areas here, which I marked, also InfiniBand systems, but the difference between those systems and the system up here is the inclusions of GPUs. And we all know that GPU and LIMPAC are not something that really goes well together. And when you run LIMPAC on GPUs, you will hit around 50% efficiencies, and this is the efficiencies that you see here. So that gives a nice view on efficiencies and answer Sharon's question or comment. Now, if taking examples of a few of the big systems in the world, and now looking from the topologies perspective, the system in China, I think it's number 3. This one, not the number 1. It's using InfiniBand with a FAT3 topology. System in Tokyo, FAT3 topology as well. System in France, FAT3. Los Alamos Roadrunner, it's FAT3. Well, it's a little bit combination, but it's FAT3. So you see the majority of the systems are using FAT3 for topology. NASA is an SGI one that they're using Hypercube with InfiniBand. Ulic is FAT3. And then Sandia, Red Sky, this is a 3 torus. So all the systems here are basically, those are the InfiniBand systems, some of the big InfiniBand systems. You see the majority are FAT3s, AGI, Hypercube, and then one 3 torus system. Now 3 torus is not new to the world, but recently you start to see more and more systems with InfiniBand on 3 torus, but still the majority are FAT3s. Now, when you talk about topologies, it's not only the clustering side, but also the storage side. So Spider, which one mentioned before, it's one of the biggest cluster systems in the world, 10 petabyte running over InfiniBand, but just giving you the notion that when you look at topologies, it's not only the clustering, but also the storage part. So from topologies, the majority of the topologies that you see today are either closed or FAT3 or CBB, 3 different names for the same thing, or mesh or 3 torus. Now, the good benefit in FAT3 is that that's the highest performance topology if you compare it to 3 torus. FAT3 can be designed in a non-blocking or non-oversubscribed manner, and it will provide you the lowest worst case latencies. Between nodes. So typically when people look for the highest performance, lowest latency network, FAT3, that's the solution. The reason for look for something else, an example, mesh or 3 torus, but if you're focusing more on the 3 torus side, is for different reasons. First, 3 torus is a blocking network. So it's not full non-blocking solution. The second thing is that in 3 torus, the worst case latency between nodes is much higher than in a FAT3 topology. Because in a 3 torus, you need to go through more hops, worst case between nodes. The reason to go for 3 torus is first, it could be cost performance question. When you build a very large systems, it might be cheaper to go with 3 torus and not in FAT3. So that's one element that you take into consideration. The second thing is, does it fit my application? If you're running an application that has locality, right? If you're calculating 3D meshes, then 3 torus will be a good option. If there is no locality in the application, and basically you run simulations that's going to connect all the nodes that exist in a system, then 3 torus might not be the option that you want to look for. And then when you think about expansion in the future, you buy off the system today, in the second half in 2 years, then with 3 torus, it's easier to expand. Much easier to add more parts of the system. In FAT3, it's durable, but that's going to take you more effort. So bottom line, 3 torus depends on the application and the performance side of things. And then there is the consideration of future expansion or cost of the system. Now, 3 torus is one example of 3-dimensional torus topology. I've put here the equation if you really want to go into the simple details of math. But the 3 torus is basically a system that each junction here is basically has 6 connections that go to 6 other junctions. And a junction, you can think of the junction as a switch junction. Now, in the case of Cray, for example, then the adapter and the switch is one silicon. In the case of Sistar, for example, and it's a junction in 3 torus. But in the simple wording, this one could be a switch, and then on that switch junction, you can put one node or one CPU or 2 CPUs or multiple CPUs, depends on what technology you're using. Yeah, this one, yeah, you're right. There's 1, 2, 3, 4, and I missed the other 2. Yes. Now, one of the good options to use, for example, InfiniBand for 3 torus is because of several capability that you can use InfiniBand for, which can give you a better flexibility or performance benefits versus other 3 torus solutions that exist. First, the way that you build 3 torus with InfiniBand, for example, is that each junction in 3 torus is a switch. And one example is that you can take a 36-port switch and have that as a junction for a 3 torus. Now, when you have 36-port switches, 36-port switches and a junction, now you're going to come into the time that you need to make a decisions on what's going to be the throughput that will go to the 6 directions of the 3 torus versus how many compute nodes I want to connect to that junction. One example is that you can connect from a 36-port switch, you can take 3 ports that's going to go to each of the 6 directions. That's going to eat 18 ports of the switch. And then the 18 remaining ports you can connect to nodes, to servers, to CPUs, to storage, for example. You can reduce the number of links from the switch that goes to the 3 torus junctions and add more compute nodes on it, which basically gives the ability to build smaller 3 toruses that achieve the same number of nodes. And that means is the latency, or the worst case latency between nodes, going to be will go down. And of course, you can reduce the throughput contention in that blocking fabric. Another thing is that on ports, you can decide to connect it to storage. And that enables you to bring storage to every junction in 3 torus. And then another item is that when you have multiple links that go to the 6 directions, you can define that one of those, for example, is dedicated for storage. And one of those is dedicated for MPI collective operations. And the rest is being used for other things. So that gives you flexibility to create or determine specific links that's going to be used for a specific reason or specific job. So if I'm putting that on a picture, imagine that this is a 3 torus junction, and then basically that's a switch. And depends on how many links you choose to have for the 6 directions. You can go from throughput with a QDR InfiniBand, you can go from 8 gigabyte to 40 gigabyte per direction. And then according to that, you can hook multiple servers or storage connections through that junction. Now, if you went with 40 gigabytes per second, then I think you're going to have 6 total connections available here. If you went with lower, you will have more ability you will have ability to connect more servers or more storage to each junction. Now, as I think Aris mentioned that before, or in the morning, in the InfiniBand world, there is a subnet management entity or subnet manager. It basically runs in the fabric and configure everything and give each node an identifier. So routing can go between nodes and so forth. Now, for InfiniBand side, there is a subnet management that fits fat trees. And there is a different subnet management that fits 3 toruses. So you definitely need to make sure that according to what architecture you built or architecture you've chosen, you're running the right subnet management for that. Now, in the last, it was done a year ago, I think, there was a development that was aimed toward 3 torus from the subnet management. Right, InfiniBand fat trees exist since 2002, so the subnet management was created long ago. The subnet management for 3 torus was done recently, so that was in the last 2 years. And I try to give you in the next couple of slides kind of a view of when you design subnet management, what are the things that you need to think about. So this is, for example, just a simple ring, but that could be a slice of a mesh or a slice of a 3 torus, just taking one connections from each or 2 connections from each. So for example, if I'm, just to take one example, if I have this configuration, and in my communication pairs, node 0 needs to send data to node 2, 1 to 3, 2 to 4, 3 to 0, and 4 to 1, and I'm taking the simple approach of minimum number of hops. Right, that's kind of simple approach. In that case, I will create blocking. And the reason I create blocking is that basically this buffer is being used to send data to this side. So this needs to go here, 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 and this needs to go here. And basically everyone can wait for the other side to go, and boom, you got blocking. So when you design lossless network, if I had a lossy network, I could just drop packets. And it's easy to avoid blocking. In a lossless fabric, you need to think on the routing and how you do it right, and just trivial routing of just going minimum hops here can create disasters or blocking. So for solving those kinds of blocking, then there's multiple options you can do. One of them is restrictive, which is if I can cut this link here, not actually cut it, but virtually ask all the nodes to not to use that link. In that case, those guys will go in these directions, but 3 and 4, since I gave him the minimum hop, will go the other side. And if they go the other side, then 4 can progress, and 3 can progress, and 2 progress, because 3 and 4 are going the other side. So that's one option. The second option is to use virtual lanes, for example, and to determine where things are going to go. And in the virtual lane perspective, what there is also described in the morning, now I have multiple lanes that goes each different directions, and I can define which lane goes in which directions, and with that solve that problem again without cutting connections that exist. Now in the 3 torus solution, so in fat trees there's multiple options for the subnet management that exist, and people can choose. And you choose, and you can choose it. Either you take the default one that exists in the subnet management, that goes with the drivers that you have, or you can modify it. to maybe do something better. For example, modifications can be to choose min hop for routing or up and down for routing. For factories, 3 torus, the preferred solution that was chosen, it's called DOR, or Dimension Order Routing. And that was the base for the standard management that was created for 3 torus. And exists out there for people to use. Now, when you go to 3 torus, and that's kind of future kind of thing, nothing basically eliminates the capability of doing different kind of topologies. One option is to do a mix topology, right? You can have a system built with 3 torus, but then if you're not using all of the links, then some of the links can be used to connect in a factory mode. And when you combine those two, then you can take all the low latency multi-process connections and run them on top of a factory, which is the lowest latency, and then the rest can go in 3 torus, which is not the right picture here. And of course, you can look on other things. But the ability of using bigger port switches as junction for 3 torus gives you a lot of flexibility. And the flexibility of building smaller 3 toruses, or the flexibility of having dedicated ports for for specific processes or network kinds. That's a great thing that goes, for example, when you use InfiniBand for 3 toruses. So a note here, a few of the things. So factory configurations gives you flat network. Oh, sorry, I'm jumping on a slide. That's a kind of a note for the coming slides, which I want to show you different configurations or examples. So for the factory is a flat network, and the following configuration, I made sure that there are not going to be any unused port in the configuration I'm going to show you. And I limit the configuration for 2 layers of switches, layer 1 and layer 2. Of course, if you want to build bigger fabrics, you can use more than 2 layers. And in the 3D torus configuration, I use the 36-port switch as the junction for 3 torus. Of course, you can use smaller switches. I think the one that Hussein is using for the hands-on system is an 8-port switch. The other side of the room, you probably noticed. You can use 8 ports, you can use 18, you can use something bigger. I use the 36-port switch as a option. And basically, from the InfiniBand perspective, as I see it, is a great technology if you're looking to build a flat connectivities that connect tens of thousands of nodes. And if you have a capability of doing InfiniBand routing, then basically you can build an unlimited size of a system. So Hussein says that he wants to build a next system. He wants to have something around 12,000 nodes. So I've designed that for you already. This is an example of nearly 12,000 nodes, 12,000 servers, using factories. In a factory, this is a non-blocking factory. So this is a 36-port switch. 18 ports goes to the servers. 18 ports goes to connections to the layer 2. If you calculating, for example, bisection bandwidth, this is basically the bandwidth here. So you take the port and double it or multiply it by the throughput, and you get the bisection bandwidth. And the bisection bandwidth here and here, it's basically the same. That's why it's non-blocking. So here, 648 36-port switches, and then 18 648 port switches here, and you have one connection from each switch to one of connection of each of the switches on layer 2, and boom, 12,000 nodes, easy, piece of cake. Now, in a factory, you can say that you don't need all the throughput, for example, and you want to go to something that is being typically called in the networking world oversubscription. In InfiniBand world, it's called blocking, but it's supposed to be the same term. You can do 2-to-1 oversubscription, which means half of the bandwidth that comes here is supported here. So if all the nodes gonna go same time, full wire speed, they will actually see half of the throughput because they're gonna be blocked here. In this case, we're on a 36-port switch, 24 ports can connect to nodes or servers, and then the remaining 12 connect to the layer 2 switching. And for this case, you cut half of the switches here, and you can do around 60,000 nodes as an example. Same option, you can go 3 to 1. More nodes towards the servers, less nodes in the less connections in the network. So in this case, if you're using 40 gig per second network, the throughput to the nodes is going to be 13 gigabit per second, assuming that everyone is communicating together, right? If that's not the case, then the nodes can see higher throughput. So that's an example to build 17,000 nodes. And I think I have one more here. This one is an 8-to-1 oversubscription, which worst case scenario going to give you 5 gigabit per second to the node, assuming you're using 40 gigabit per second network. And now with 2 switches here and 24 here, you can do a 10,000 node system. So those multiple configurations on the factory, and then an example on 3 torus, 36 port switch here, using 3 links from the switch for each direction of the 3 torus. That eliminates 18 ports of the switch. Then the remaining 18 ports each connect to a server. And that gives you with an 8-byte, 8x8 3 torus size, ability to do around 10,000 nodes. Now, if you're using something else for the 3 torus junction, which limits how many CPUs you can put here, then for the same size of CPU cores or nodes or sockets, then the size of the 3 torus would be much, much higher. Which has impact on latencies and blocking and some other elements. Here with 8x8x8, which in all reasons is a small 3 torus configuration, you can do around 10,000 servers. And that's from a mapping from a switch perspective, which I stole from an OEM. In this configuration, you see the 3 links basically going to each of the 6 directions. And then the rest are on nodes. I think I'm missing one here. And then, of course, you can do an IO node as well as one of the connections to the 3 torus junction. So that's the summary for the topology. So when you come to choose which topology you want to use, first you look on the application perspective, and if there is locality, great, 3 torus can be a great option. If there is no locality, then it's going to come to the price performance issue. Multiple users, multiple applications. In that case, then I would guess that some of them might have locality, some not. And in this case, you probably want to look more in the factory. And if you want something that it's non-blocking, that's a factory. There is no question about that. And that the cost. Cost depends on the size of the systems and how much you can squeeze from the vendors. So if you can do good negotiations, then you're good here. If not, then it depends on the size and the cost. And very large systems can be cost effective with 3 torus, and someone asked me what's the size of the system. So there is no kind of a size. It more depends on how good you can do negotiation. So if you can do good negotiations, you go towards the high part of thousands of servers. If you can do bad negotiation, that's something else. But then you need the different sessions to learn how to do better negotiations. And if you look on future extensions, then 3 torus might be a good option, because it's kind of easier to just add more nodes into it. So that's the reason for that, and I think that completes the topologies. I wanted to give you one quick slides on offloading. Just to tease you, I wanted to. Yeah, so fat-trace or closed or CBBs, and 3 torus or 2D meshes, other element, those are the probably most used topologies right now. People constantly looking for other topologies. One of the things that is being looked more for some vendors, less for some other vendors, really depends. Looking at the entire market was broad butterflies and specific kind of butterflies could be dragonflies and other kind of animal names. So that's something that people always look, and if it makes sense, it makes sense. Now, from a performance perspective, for example, butterflies or dragonflies doesn't give you better latencies than fat-trace. So if you're looking for the lowest latency connections, and you're looking for full non-blocking, then there is no real reason to go to the flies family. You can go with the fat-trace. If you're coming from a 3 torus side, then you can try to look into improving 3 toruses from a blocking and performance perspective. And this is dragonflies, butterflies, things like that. But again, the question is the performance and your needs. And right now, the variety that exists is very nice. So I'm on time. Time okay? 5 minutes is good. So I wanted to give you one quick slide on offloading. I don't know if DK was here. Disappeared. Outside? So you might be talking about MPI offloading and stuff like that. I wanted to give you a quick view on why offloading of MPI operations, or one example is collectives, but it doesn't mean only collectives, can be of a great benefit. And I want to look into not MPI 1 or 2, but I want to look into MPI 3. Which DK also indicates as something that is being worked in the MPI form for creating the specification for MPI 3. One of the things that will be part of MPI 3, it was already defined, already written, already voted on and already approved, is non-blocking collectives. And our collective, MPI collective, is operation that is being used for synchronize or send data or gather back data. So that's a multi-node, multi-process operation. And when you go to the multi-process operation, then you definitely want that to be done as fast as possible. And today, majority of the usage is with blocking collectives, which means that once you start an MPI collective operation, till it finish, nothing else can happen. And that's definitely when you go to the large scale, it's not a great solution because then you can hit performance limitations or degradations because of system noise and jitter and some other effects. With the MPI 3 specification, one of the things that is there, it's doing non-blocking collectives. And non-blocking collectives gives you ability to do the collective and at the same time go and do something else. And that's a great drive to look into offloading collective operations outside of the CPU to something else. And the reason is that even if you have a non-blocking collective, if the CPU is the entity that does and manage the collective operation, then you don't gain all the benefits of doing non-blocking. Right? The whole idea of non-blocking is that I just launch the collective and then something else is going to do it for me. And that's the reason that you see out there technology that comes out to offload collective operations. And that's a graph that I stole from a paper that was presented by Oak Ridge National Labs. That was one of the early first results in their work. And what they did is they create a simple application. And a simple application does compute and then barrier. And then compute and then barrier. And basically, the compute was set by basically running a busy loop. So you run a loop of time, and then you do barrier, and then you do another loop with the CPU, then you do another barrier. And this is the time per operation. This is not the time for the collective. This is the time for the complete operation, which is the busy loop and the barrier. And then a quick run from running collectives on the host. Now again, this is a non-blocking collective, which is going to be part of MPI3, but that's non-blocking collectives runs on the host. So the CPU does everything. And basically what we try to measure is CPU availability, which means how much of the CPU I can really dedicate it for the actual compute side, instead of having the CPU being dealing with the actual work of the collective operation, which is the overhead. And here you see that first, if you move the collective operations outside of the CPU and give it to the network to deal with, then you reduce the runtime of the operations, which is very nice. But more important is that when you start to increase the busy loop time, or you increase the computations that I need to be doing for every cycle, then pretty much runtime goes up dramatically when you're running from the host. And the reason is because the CPU needs also to deal with sending the data out. And it's blocking other elements that exist. And pretty much you go to like 50% CPU efficiency, and your runtime become too big. And then if you keep the collective work outside of the CPU and give it to the network, then basically you can go here. It's nearly 90%. And I think right now it's even better than that. That was one of the early graphs. But you can go to around 90%, and there is no change of the runtime. So think about it. In average, if you want to keep a normal runtimes, you would keep the CPU 20, maybe 30% busy with computations, and the rest gonna be the network side of the collective gonna eat the CPU cycles. Here you can go and stretch the CPU work to 90%. Yeah.
So, can you give me an insight how
So you kind of mix between two different things here, I think, or maybe I got it wrong. But the way or how to move collectives from the CPU out to the network, there is multiple views of it. For example, back when Quadrix were alive, they had the offloading that was mostly in the switch and part in the adapter kind of things, but it was more on the switch side. On InfiniBand side, there is a couple of vendors that do combinations of offloading to the network and doing some in the switch. But that's from the offloading perspective. And if you do it right, then you will not limit scaling, or you will not limit scalability. The thing is that if you look on the adapter side, on the network side, the network adapter knows how to handle throughput in wire speed. Else it wouldn't be 40 gigabit per second, right, or more. Now, if the same hardware can deal with the collective operation at the same speed of the traffic coming in, then I don't really care how many cores are being part of that collective operation. As long as I can handle wire speed and handle all the collective operations in that wire speed, there is no limit. So if you do it right, then you won't create extra issues of scaling. So that's my last slide. Before I go, if there is any questions on the two items.